Let's look at how to approach problems associated with kinetic energy and work. Let's look at the following problem. An object with mass 80 kg, that is this object, has an initial speed of 35 meters per second. A force slows it down at a deceleration of 2 meters per second squared. So as it moves to the right, it is slowing down, and the deceleration is 2 meters per second squared, or acceleration in that direction is 2 meters per second squared, meaning the object is slowing down. Find the magnitude of the force, the distance the object travels while slowing down, until it stops, that is, and the work done on the object by the force. Now, part A is straightforward. We want to determine the magnitude of the force that slows it down at a deceleration of 2 meters per second squared. The mass of the object is 80 kg. So, according to Newton's second law, the magnitude of the force is mass times that acceleration. So the mass is 80. Acceleration, or deceleration in this case, is 2 meters per second squared. So you get 160 newtons. What is the direction of this force? The same as the direction of the acceleration, namely to the left. Part B. Calculate the distance the object travels while slowing down. So it has an initial speed of 35 meters per second, and after traveling a distance L, it slows down and comes to a complete rest, meaning the speed is now 0 meters per second. What is the distance traveled L? We can use the work-kinetic energy theorem to solve this problem. Work-kinetic energy theorem says work done by a certain force equals the change in kinetic energy that results. The final kinetic energy minus the initial kinetic energy. Now we know the final kinetic energy is 0 because at the end it comes to a complete rest. So when speed is 0, kinetic energy is 0. The initial kinetic energy is minus. Minus is from the difference that we talked about earlier, which is embedded or part of the work-kinetic energy theorem. The initial kinetic energy is half times the mass, which is 80, times the square of this initial speed, which is 35. So we square that. Now let's compute the work. Work is done by this force, which is heading to the left. The displacement is to the right. So it is given by dot product of that force, which we know the magnitude of, is 160 newtons. The direction is minus I hat, because if this direction is minus I hat, that direction is I hat. The displacement is L, so you dot it into L, I, hat, because this displacement is along that direction. Keep in mind, work done by a constant force is a dot product of that force and the displacement that is being carried out. So finally, equating the left and the right, we get 160L equals 40 times 35 squared. And we can determine what L is. And if you do that, you get 306 meters. So that is the distance the object travels before come to a complete stop. Now let's do part C. Work done on the object by the force. Now we know work is a dot product of two vectors. One is the force, and the other one is displacement vector. So the force is 160 newtons, so minus I hat direction, dotted into now L, we know what it is 306 I hat meter. So when you do the dot product, we get a negative result for the work, which is minus 48,960 joules. The minus sign indicates the direction of that force and displacement are opposite to each other. Another conclusion that can be reached from this negative sign for work is that the kinetic energy decreases, meaning the final kinetic energy is less than the initial kinetic energy. A second problem. A mass 10 kg attached to a string is lowered from rest with a downward acceleration of 2.5 meter per second squared. So this is the string, and the mass is 10 kg, so the weight is 10 times gravity, and there is tension acting in an upward direction, capital T, the tension in the string, that is. The acceleration is downward, 2.5 meter per second squared, and it falls a distance of 3 meters. Find the work done by the string's tension, that is by this force right there on the mass. Let's first determine what the value of the tension is. Now, from this free body diagram, we know the acceleration is downward, so the net force is 10g, that is the weight, minus the tension, and net force is m times a. M is again 10 kg, acceleration is 2.5, which is 25. So T, or the value of tension in the string, is 73.1 Newton. So the work done by this tension is that tension force dotted into displacement which we are given. So tension, the force is acting up, let's call that direction j hat. Displacement is downward, so it's minus j hat. So putting everything together, the tension will become 73.1 j hat dotted into minus 3 j hat. And you will get minus 219.3 joules. That's the work done by the tension. Now part B, work done by the gravitational force. Work done by the gravitational force is work done by the weight, that is. The weight is moving downward, so it's minus 10g j hat. The displacement is also downward, minus 3 j hat, because the magnitude of the displacement is 3 meters. And you're going to get positive 294.3 joules. Now, kinetic energy of the mass as it get to that level. So it will be moving with some speed, let's call it v. So it has certain kinetic energy. What is the kinetic energy of that mass when it has fallen through a distance of 3 meters? So that's part C. So of course it starts from rest, so that's initial state, and that is the final state. So the final kinetic energy minus the initial kinetic energy is the work done, the net work done on this mass. The net work done equals the net force dotted into the displacement vector. Kinetic energy initial is 0, so that goes away. So the final kinetic energy, or the kinetic energy at that 3 meter point, equals the net force. The net force is ma according to Newton's second law. We know the mass of this object, 10 kg. We know the acceleration, 2.5. The acceleration is downward, so the net force is also downwards. Let's call that direction minus j hat, dotted into this displacement vector, which is again minus 3 j hat, because the displacement is also downward. So what you'll get, 10 times 2.5 is 25. 25 times 3 is 75 joules, because minus j dotted into minus j is 1. So that's the answer for part C. Now part D, what is the speed of the mass at that point? Kinetic energy, which we have found to be 75, equals half times the mass, which is 10, times that speed at that point squared. And you can find the speed, which is quite simply 3.87 meter per second. So that's the answer for part D. The third problem. A force F equals to minus 6xi hat newtons, axis measured in meters, is acting on this body, the mass of which is 2.5 kilograms. The velocity at this point at x equals to 3 is 8 meters per second. Find the velocity of the body when it gets to x equals to 4 meter mark. If you note, the force is a variable force, meaning it is dependent on x. It's not constant force. So when we apply the work-kinetic energy theorem, it will be in this particular form. So the work done equals the change in kinetic energy. So this is the final point, and that is the initial point. So the kinetic energy at x equals to 4, subtract the kinetic energy at x equals to 3 equals the work done by this variable force. Now, work done by this variable force is given by an integral, like that, between the limits in this case, 3 to 4, as the object moves from 3 to 4. So let's put the force in. The limits are 3 and 4. The force is minus 6xi hat. Note that when you dot it into displacement, dxi hat, you get pretty much that result. So in this case, you get 4, 3 as the limits, minus 6x dx. Note that the kinetic energy at x equals to 4, you can simply write it as half. The mass is 2.5 kg. The speed is what we want to determine. So we have v4 squared. Subtract this kinetic energy at x equals to 3. Again, half, mass is 2.5. Now the speed we know, and that is 8 meters per second. So 8 squared, so that's 64, equals this entire integral. When you integrate minus 6x, you get minus 3x squared. We have to put the limits 3 and 4 inside, which if you do, you get minus 3. 4 squared is 16, minus 3 squared is 9, so you get minus 21. Equating this side to minus 21, you can solve for v4, which is the only unknown here. Solving for v4, we get 6.87 meters per second, and that is the answer for part A. Part B. At what positive value of x will the body have a speed or velocity of 6 meters per second? Let's assume it occurs here at some value of x. Let's call it x bar. So the kinetic energy there is the final kinetic energy. We can compare the kinetic energy there to the kinetic energy at x equals to 3. So the kinetic energy there is quite simply half times mass. Mass is 2.5. The speed we know is 6 meters per second. So square that is 36, minus the initial kinetic energy is half, 2.5, and the speed there is 8. So square that is 64, equals the work done by that force, which is minus 6x dx from x equals to 3 to that unknown point x bar. The left hand side is minus 35. Now let's calculate the right hand side. It's going to be minus 3x squared with limits x bar as upper limit and 3 as the lower limit. So substituting these limits in here, you get minus 3x bar squared plus 27. In solving for x bar, you get 4.55 meters, and that is the answer for part B. Thank you for watching.